in last discussion about SVD, हम लोगों ने क्या देखा था कि we have a set of eigen values and eigen vectors. ठीक है, तो so first thing we have to see here is what is eigen value, what is eigen vector. Eigen value, eigen vector. ठीक है, okay, and why do we use it, what is the need of using it, and what is eigen decomposition basically. Decomposition and what is SVD. ठीक है, so we are going to discuss these four today. अब first thing we have to understand about eigen values and eigen vectors is that suppose I have a set of vectors or some value that I want to calculate as, let's say, so yes, so so let's say first thing what we want to do is we have to we have a vector that is I can represent a vector like this in x and y dimension. Suppose this is 1 2 and 1 2 3, so this is my vector somewhere over here, it is somewhere over here. ठीक है, so this is my vector 2 3. Now what I want to do is I want to scale this vector and I want to transform it into some other vector. ठीक है, so for transformation we know that we have a set of matrices. When we multiply any vector with that matrix, we get some matrix, and that is transform matrix. So this is our transformation matrix that we apply, let's say A, to this vector V. So here vector is 2 3. So it's, I would say it's, I can write it as 2 3. ठीक है, let's see my transformation matrix is 0. So this is, let's say, my transformation matrix, and this is my vector V. Now I want to scale it, so I'll multiply this it with a transformation. So any scaling matrix is represented, because this is, we have studied in graphics that whenever we multiply any diagonal matrix by any vector or any matrix, so it will give me a new vector or a matrix that is a scaled version of the original one. So if I multiply it with this, I will get I'll get 2 and ठीक है. So you can see, so this is my new point, that is new vector, new or transformed vector, transform vector. So my original vector V, that is transformed to V dash, and which is from 2 3 to point this over somewhere here, that is over 4 5 6, so over here. ठीक है, so this is 2 6. ठीक है, तो the idea behind matrix multiplication is that we are multiplying with a suitable matrix that will convert my original vector into some other scaled vector or maybe rotated vector. So for rotating we have some other matrix and we can multiply with it and we get a new rotated vector. ठीक है, so that is why we are doing a multiplication. So multiplication is basically to change the to transform the original vector into a new vector. ठीक है, अब इसके बाद we have let's say this is, we are talking about only one vector. Suppose I have a set of vectors like this. This is 1, this is 1, this is 1 1 and so on, 1 comma 1, sorry, minus 1 comma 1, this is 1 comma 1. So all these points are 1. ठीक है, this is minus 1 and plus 1 and plus 1. ठीक है, so this is my first vector, let's say A, and this is my second vector, let's say B. So what I want to do is I want to scale this. So all the vectors that is represented in this rectangle, so all the vectors would be scaled. So any vector that is, I'll draw it with another pen. Let's say this is one vector, another vector, another vector. So all such vectors would be scaled, right? So if I'm scaling this, that is I'm multiplying it with some transformation matrix. So I'll get some new set of vectors whose values would be something else. So this is my A, this is my new A dash, and this is my new B, that is new B dash. So what you can see over here is, but this vector, suppose I have scaled in both horizontal and vertical directions. Suppose I scale it in, let's say, in only in horizontal direction or only in vertical direction. So if I am scaling it only in vertical direction, it will look something like this. Okay. So now you can see that A dash is changed, but B is the same. Okay. And this vector, let's say this vector, I'll call this as C. So C would also be changed. So it is shifted to somewhat this position. If I'm scaling it, so the original vector would be shifted. So basically angle of this would be, angle of C vector would be shifted to some other position, maybe this or maybe this, something like that. So this angle would be changed. So basically what I'm trying to say is, for A and B, if I'm transforming a set of vectors into another dimensions or another set of vectors, so if I'm transforming it, some vectors are there which remains unchanged. So B is unchanged here, you can see, while rest of all the other vectors are changing. So for example, this is again my set of vectors A and B, and if I'm scaling it in the vertical direction, this is changed to somewhere like this. It would be somewhere, so this angle would be more theta dash, and this angle for this would be theta. Okay, something like that. And this A is same, and B is changed to B dash. Okay, so this A and B are called eigenvectors. Vectors of this original set of vectors. Why A and B are called the eigenvectors? Because A is unchanged and B is also unchanged, but only magnitude is increased. Okay, so that is why we call such vectors whose basically magnitude can change, but which remains the same. So those vectors are called the eigenvectors. Okay, and the value is called for new vectors, it is converted to B, it is converted to A dash, and it is converted to B dash. But A dash is same as A, and B dash is, let's say, same as 2B. So eigenvalue for new vector is for A dash is 1. Eigenvalue is for new A dash is equals to 1, and eigenvalue for B dash is equals to 2. Why? Because magnitude is increased to 2B, and magnitude is increased to 1A, that is original A. Okay. So such vectors whose basically angle doesn't change, angle remains the same. For rest of the vectors, angle would change. So for those vectors, angles doesn't change. Those vectors are called as eigenvectors. So this is the idea behind vectorization, behind calculating the eigenvectors. Another example is, suppose I have a matrix. Let's say I have a set of vectors. They look like this. Okay. And I'm rotating this. I'm performing some rotation. Okay. Rotation means I'm again multiplying it with some transformation vector t, and I'm saying that okay, I have got a new rotated vector that looks something like this. So in this scenario, there are no eigenvectors. Why? So somebody is requesting for control. Anyway, so this is no eigenvectors. Why? Because all the vectors are changed. All the vectors in all the directions are changed. So A is changed to something, let's say this is A, new A, and this B is changed to So all the vectors are basically rotated. So that is why this matrix has no eigenvectors. So what is the advantage of doing this? So whenever I have some matrix represented by a vector or a set of vectors. Yes, somebody wants to say something. So if you have any questions about quiz, please ask later. अभी let's continue with whatever we are doing. ठीक है? तो इसमें what we want to do is we want to basically find out the transformation. So what are the steps to do so? Hmm? Okay, please. Please don't disturb, okay? चलो. Now let's see how do we calculate eigenvalues and eigenvectors. So in first class we have seen that we have this AV is equals to lambda V. Yes, Amit, you have any question? Okay. So in first class we have seen that AV is equals to lambda V. So this is what we are doing here is V is the vector that we want to transform. A is the transformation matrix, and lambda is the eigen value, and V is again the same vector. Okay, so my eigen decomposition says that whenever I am multiplying any vector V with a matrix A, it will be same as I'm multiplying the eigenvalues with a vector V. So it would be the same. So if I can write this as A minus lambda I, because I is a identity matrix, lambda is a scalar, and A is a matrix. So A is a matrix, lambda is a scalar, and this I is again identity matrix equals to 0 if I am taking this right term over the left. So we have seen that. ठीक है? So from this equation we always calculate our eigenvalues and eigenvectors. ठीक है? So let's say take an example. How does this work? Suppose I have a equation, suppose I have a vector A that is a transformation vector, and this vector will transform any matrix to some new set of vectors. So sorry, this is a matrix, not a vector, it's a matrix. So this A will transform any set of vectors to a new set of vectors. Okay, now I want to identify the eigenvalues for this matrix. So what I'll do is A is, let's say, 1 0 0 and 2. Okay, and if I want to find eigenvalues, what I'll do is I will put this portion into characteristic equation, which says that A minus lambda I is equals to 0, and I is the identity matrix. So it would be, and A, I know that what is A. So this is 1 minus 1 0 0 2 minus lambda of identity matrix is 0. This is 1 and 1, 0 and 0 equals to 0. Again, if I subtract it, I'll get 1 minus lambda 0 0 2 minus lambda equals to 0. So if I calculate the determinant, is equals to 1 minus lambda into 2 minus lambda is equals to 0. So I'll get lambda as 1 comma 2. So these are my eigenvalues. Okay. So from this, I have eigenvalues of 1 and 2. Okay. Now, suppose I want to find out the eigenvectors of the same problem.
And why did you take determinant?
Yes, so this characteristic equation is like this. I have not written it. We have discussed this earlier also. So it is basically like this. A minus lambda I whole determinant. Because A is a matrix and 0 is a scalar. So we want to convert this whole matrix into scalar. So that is why we take determinant. Determinant
Okay.
of this whole part. Okay. Okay, now we have eigenvalues. Now we want to identify the eigenvectors. So whenever we want to identify eigenvectors, calculation. So if we want to calculate the eigenvectors from the eigenvalues lambda 1 and lambda is equals to 1 and lambda 2 is equals to 2. So two eigenvector values we have. From this we want to identify what is our eigenvector. We know that our A is our matrix, original matrix was 1 0 0 2. Okay. So so what I always do is I first for lambda is equals to 1. For this what I do is I calculate A minus lambda I. So this is 1 minus 1, 2 minus lambda is 1. So 1 and 0 and 0. Okay, lambda is 1. So it would be again okay. So for this you have to understand that A minus lambda I determinant is 0. That equation was coming initially when we have derived that equation. It was I'm writing this A minus lambda I is equals to 0. This equation was coming from Ax minus lambda x, right? So this was basically no, it was from Av minus lambda v. This was coming from initial equation was Av is equals to lambda v. Okay. So I can write this as Av minus lambda v is equals to 0. I can write this as A minus lambda I and v as 0. Okay. This v can be this v is the basically eigenvector. So it cannot be 0. That is why we are putting this A minus lambda I to 0. Okay. So this is from here we are putting this lambda I to 0. Now v is the eigenvector originally. So while calculating this value, we have A minus lambda I into v over here. This is v. We want to calculate this v. Okay. So it is it will look something like this. 1 minus 1. This is 0. This is 0 minus 0 0 0. And 2 minus 1 is 1. So v. Now this v is again eigenvector. So it can be, I can write this as v1 or v2. Okay. So this is something like 0 comma v2. So this is my first eigenvector for lambda is equals to 1. So this, what does this means? That this means that any vector that is on the line 0 2. So this is over here 0 and 2. This point is 0 comma 2. Sorry, this point is 0 comma 2. So 0 comma v2. Any v would be over here. So any vector that is on the y direction would remain unchanged if I have this transformation matrix which looks like A. So this is the transformation matrix for a scaling problem. So we have already seen that for a scaling problem, my horizontal and vertical vectors remain same, only their magnitude changes, right? So this is what this whole is representing. Okay. So this is my first eigenvector for lambda is equals to 1. Similarly, I can calculate for lambda is equals to 2. For lambda is equals to 2, I'll calculate and I will get something like v1 and 0. So this is my second eigenvector. eigenvector. ठीक है, so which means that any vector that is in this x direction is my eigenvector because it remains unchanged when I perform scaling operation with this matrix that is given over here. So I hope eigen thing is clear right now. Okay, if it is not clear, I'll explain it in the next class. I wanted to finish SVD but we don't have time right now. So ठीक है, तो ये वाला पार्ट समझ में आया है कि नहीं? यू कैन, आई क्रिएट अ पोल, आप लोग पोल कर सकते हो, और नहीं समझ में आया तो यू कैन, आई शेयर नोट्स एज वेल. ठीक है, we don't have time right now, so we'll discuss SVD part. So basically अभी हमने जो देखा that was eigen, calculating eigen values and calculating eigen vectors. ठीक है, in next part we'll see how eigen decomposition and how SVD is related to this. ठीक है, okay, so I'll download the attendance. I have searched so many things to explain this eigen decomposition because there is so much material available, but most of it is very complex. So I have tried to search the simpler thing so that you people can understand. So if you have